Hello everybody. So in this video we're going to solve one more example about the energy balance on partial vaporization or partial phase change. So in this case we have acetone which is feed to this unit. It's not pure acetone, it's acetone with nitrogen, so it's acetone vapor. It's a 66.9 mole percent acetone vapor, and the balance is nitrogen, and the process is shown. We have here the acetone, and the nitrogen is fed to the condenser. And this goal of this whole process is to separate the acetone from nitrogen. And one easy way of doing this, since there is a very big difference in the boiling points, is to condense the the less volatile component, which is acetone. So if you cool it, you can condense only acetone. Nitrogen is not going to condense at 5 atmospheres as it's shown here. So only acetone is going to condense, and nitrogen is going to come out with very high concentration. It's 90 point something percent, almost 91%. And we recovered all the nitrogen in the top product. Part of the acetone escapes with the vapor stream, but the most of acetone is recovered in the liquid stream. You'll see here this is 66.9 moles of acetone here in the feed. We have 63.5, which is very big amount of it. It's more than 95%. So what we need to do is to know how much heat is removed from the condenser in order to achieve this separation. So it's very similar to the previous example, and I believe it might be a little easier because in this case we have only one component in the liquid stream. So anyways, we'll go with the same procedure. Luckily we don't have to do any mole balance, so all the mole fractions and all the number of moles are given. The energy balance equation, after canceling the zero terms, which are the work, because it's a condenser, we don't have any work here. We can ignore the effect of change of kinetic and potential energies, so the equation reduces to Q equals delta H, and delta H is the enthalpy of product minus the enthalpy of the feed. So the product is acetone liquid multiplied by its flow rate. Of course this is the specific enthalpy, and the same, this is the flow rate of the acetone in the top product, which is the multiplication of the mole fraction multiplied by the total flow rate, multiplied by the specific enthalpy of acetone in the vapor, the same for nitrogen in the vapor, minus the number of moles of acetone in the feed multiplied by the specific enthalpy of acetone in the feed, and the number of moles of nitrogen in the feed multiplied by the specific enthalpy of nitrogen in the feed. So we will do the same thing. We will construct the enthalpy composite, the inlet outlet enthalpy table. So in this table we have all the flow rates which are listed here. We will take the feed conditions as the reference conditions. So in this case the enthalpy of acetone and nitrogen are both going to be 0 in the feed stream, of course, and then we will have the product stream containing the three components, 2 vapor, acetone and nitrogen, and 1 liquid. By a very quick look at this example, you would see that we have 2 terms that would be easy to calculate, because in this case we have gas that is turning into gas, or vapor turning into vapor at different temperatures, so we don't have any phase change, which would make the calculations easy. The one that would take more time, which is the one in the liquid phase. So we have to construct the hypothetical path. So for the hypothetical paths, we will do one for acetone in the that would be in the liquid stream, and one for acetone in the vapor stream, and one for nitrogen in the vapor stream. Keep in mind that the feed conditions are the standard conditions, or the reference conditions, I'm sorry. So the reference is vapor at I don't remember the temperature. It was at 65 degrees Celsius and 1 atmosphere. So so I'm going to go for the acetone from vapor at 65 degrees into acetone vapor at 20 degrees Celsius and 5 atmosphere, which is the this acetone. So it's here there are two changes. One is change in temperature and one is change in pressure. So the change in temperature is going to or these two are going to be in two separate steps. One which is the change in temperature followed by the change in pressure. So I'm going to call them delta H acetone 1 and delta H acetone 2. The same for nitrogen, but let's go for the other acetone. So I'm going to have acetone vapor at 65 degrees Celsius and 1 bar, and then it will turn into acetone liquid at 20 Celsius and 5 bars. Again, since we have phase change, we have to first look at the available information about the latent heat of vaporization. So the latent heat of vaporization is available at the boiling point. I don't know, maybe the boiling point is 65 degrees Celsius or 20 Celsius, I don't know. So I have to look it up and check where is the, what is the value of the latent heat of vaporization of acetone, and I mean the boiling point of acetone, I'm sorry. So this is acetone, the boiling point is 56. So it's neither 65 nor 20, so we have to go from 65 into 56, and then the latent heat of vaporization, and then do the rest of the steps. So that's why we will take the first step as this. Of course, 1 atmosphere and 1 bar are almost equal. 1 atmosphere is 1.013 bars, which is almost 1-to-1 ratio. So this very small change in pressure is going to have no effect on the enthalpy. We have seen this many times before in cases we had 5 bars or 4 bars of difference. It had very minimal effect. So the difference between 1 bar and 1 atmosphere is going to be 0. I can confidently say it's going to be 0. So we will ignore the difference between 1 bar and 1 atmosphere, and we'll assume that this is only one step, which is the change in temperature. Then at 56, which is the boiling point, we can put one step of the phase change, and then we have from here to there we have 2 changes, one in temperature and one in pressure. So the one in temperature is going to be from 56 to 20, and the pressure from 1 atmosphere to 5 atmospheres. And then we have 4 enthalpies in this hypothetical path. Finally, for nitrogen is going to be exactly similar to what we did in acetone vapor. 1 change in temperature and 1 change in pressure. So we have 8 enthalpies to calculate. Before we proceed, there is something that is going to be good news for us, that we know that the pressure difference has no effect on ideal gas enthalpies. So the step of changing the pressure here and the step of changing the pressure here are going to have 0 delta H. Because in this case the change in enthalpy is not a function of pressure, the change of enthalpy is not a function of pressure. So the I mean here yeah, oh, I think there's something wrong here. So this should be 65 degrees and 20 degrees and 1 bar. This should be 1 bar, I'm sorry, and please fix this. Is 1 bar, I'll fix this, but this is 1 bar. So let me put it now before I forget. Type. So this is 1 bar. So the change in pressure here and change in pressure here are going to be zeros. So we're only going to consider the 6 steps. So let's go for the first 2, which are the vapor stream. So the vapor stream delta HC1, which is the acetone 1 from 65 to 20. We have here already the constants of Cp for acetone. This is just change in enthalpy due to change in pressure, so it's going to be the integral of Cp dt. So from 65 to 20, of course, for the gas phase. I didn't do the substitutions because it's a straightforward thing, so you can do this yourself. And again, once you are done with the hypothetical path, you are almost done with everything. So you just need to do the calculations, picking numbers from the table, and all these routine things. So this is for acetone, and then for the second one for acetone is going to be 0, because we know that this is independent on pressure. So you can calculate the enthalpy of acetone in the vapor phase is going to be negative 3.61. The same for nitrogen. We will substitute with the constants of nitrogen, and then the second step is 0. Finally, we can get the enthalpy of nitrogen in the vapor phase. So this is I think I put the wrong values here, but anyways, yeah, this is this should be the acetone constants. But anyways, so we have the enthalpy of acetone in the 4 steps. The first is going to be the change in temperature of liquid acetone. So we're going to put the constants of liquid acetone, vapor acetone, from 65 to 56. Then the latent heat of vaporization, which is negative 30.2. You can find it in the previous slide. I just put this in the right place, so it in the wrong place. So this is 30.2. But keep in mind that this is a condensation. So this latent heat that we have here is a latent heat of vaporization. In this case, it's condensation. So it's the opposite process. So the direction of heat is going to be the opposite. So I just put the same number with an opposite sign. So that's why we put it as negative 30.82. Then the next step is the integral of Cp dt for liquid acetone, which are only 2 terms, which are easier to deal with. Finally, we have the last one, which is the effect of pressure. This is not 0, because we know for liquids it's V hat delta P. V hat delta P, we can get V hat from the 1 over the specific gravity. This specific gravity is what we can get from table B1. This is the specific gravity, 0.791, which is this value. And we multiply by 1000, so it's kilogram per meter cube. We use the molecular weight to convert it into meter cubes per kilomole. Then we multiply by delta P, which is P2 minus P1. Then I multiplied it by 1.013 times 10 power 5 to make it Pascal, divide by 1000 to make it kilopascal, and after this we can multiply kilopascal by meter cube. So we know that Pascal times meter cubes is joule. So kilopascal times meter cube is kilojoule. So that the result is going to be kilojoules per mole. And then per kilomole, I'm sorry, because it was kilogram originally. So after molecular weight, it's kilomole. So if you convert this into kilojoules per mole to match the units of the rest of the terms, it's going to be 0.02975, which is very, very, very small number. And again, this confirms what we said before about the minimal effect of pressure on the change in enthalpy. We have here, let's say in the previous step, we have 36 degrees Celsius, which is not a big deal. 36 degrees Celsius change in the temperature has an effect on enthalpy is negative 4.682, while for 4 atmospheres, which is a huge pressure difference or a very big pressure difference, it's making very, very small effect on the enthalpy. So anyways, there's something we can ignore. We can assume it's 0 without going into through this hassle of unit conversions and all these calculations. Finally, you can get the enthalpy of acetone in the liquid stream, which is the summation of all of these terms. Finally, you can put everything in the table and substitute with the numbers, this multiplied by this, plus this multiplied by this, plus this multiplied by this, which is what we have here, minus this by this, and minus this by this, which gives us the final enthalpy in the heat removed in kilowatts. So this is all for this example. Next video we'll start with another topic, inshallah. So you'll see you then. Goodbye.